Good evening, everyone. My name is Jonathan, and today I am presenting my third lab, which focuses on black holes. So this was a two-part lab, and our objectives were to determine the mass of a black hole, as well as to calculate the velocity required for a spacecraft to orbit as close as possible without succumbing to the gravitational pull of the black hole. So to simulate this, we used all of our coding in GlowScript and integrated a couple of physics concepts to get to the bottom of our question. So in our initial phase, we used Newton's second law, an important foundation of physics. And by employing the momentum principle as well, we dissect the forces, parallel and perpendicular components. This approach helps us for a comprehensive understanding of the interplay between gravitational forces and the motion of objects in our universe. Another important concept that we used in this lab was the law of universal gravitation, which enables us to quantify gravitational forces exerted between objects. Through iterative processes, I computed the mass of the black hole, averaging values obtained to get a sort of close, precise estimate, and our result revealed that the mass of the black hole was approximately 1.607 times 10 to the 34 kilograms. And as you can see, that is pretty dense, pretty heavy. Now in part 2, with the mass of the black hole established, we can start calculating the trajectory of our spacecraft orbiting in the near vicinity. And through experimentation, we determined that the velocities for the spacecraft to navigate close to the black hole without succumbing to it and getting sucked in. And we saw that the velocities given was a negative 9 times 10 to the 7 and a 9.9 times 10 to the 6 meters per second in the X and Y direction, respectively. And as we can see, this is in tandem with the motion of the black hole that we're looking at. Net forces on the planet and ship were computed by summing the gravitational forces between them and the black hole. Position and velocity updates were then applied to the model their motion, and the calculated velocities ensured the ship could approach and exit the system without being sucked into the black hole. So when looking at possible errors in this lab experiment, one of the big things is that we excluded other space forces that may come into play. And on top of that, our mass for the black hole is assumed via averaging multiple masses. So because of this, our calculations aren't 100% accurate given a real world situation. So for instance, if someone were to actually go fly a spacecraft near a black hole, I wouldn't recommend basing their plans off of this experiment. In understanding the differences between net force and momentum, momentum involves measured velocity and mass, while net force and its components are derived from instead a calculated momentum. And so to conclude here, to establish an orbit around the black hole that we looked at, the initial velocities of 1 times 10 to the 5th and 1.2 times 10 to the 7 meters per second were found for the ship in the X and Y directions respectively. As we can see, basic concepts and laws came into effect here, such as Newton's second law and the momentum principle. And we are amassing average masses and predicting trajectory using gravitational force. That is all. Thank you so much for your time.